Welcome! In this video, we'll tackle an exciting coding challenge, LeetCode problem number 864, shortest path to get all keys. This problem dives into graph traversal and optimization, combining BFS with some unique twists like handling keys indoors. Get ready to sharpen your problem-solving skills as we explore different approaches to solve this challenge. Let's get started. In this problem, you are given a 2D grid that represents a map. Each cell in the grid has a specific meaning. A dot, represented by dot, indicates an empty cell where you can move freely. A hash symbol, hashtag, is a wall that blocks your movement. The @ symbol marks your starting position. Lowercase letters, from A to F, represent keys that you must collect to unlock certain locks. Corresponding uppercase letters, A to F, represent those locks, where, for example, the key A unlocks the lock A. You can move one step at a time in any of the four cardinal directions, up, down, left, or right. However, you cannot move outside the grid or pass through walls. Once you collect a key, you can use it to unlock its matching lock, and the key can be reused without limitation. Your task is to find the shortest path that allows you to collect all the keys. If it's impossible to collect all the keys, you should return -1. The output of the problem is represented as an integer. This integer will be the shortest number of steps required to collect all the keys on the grid. If it turns out to be impossible to collect all the keys, your output should simply be -1. Let's look at a concrete example. Suppose the input grid is as follows: @a hashtag BAB. Starting from the @ symbol at the top left corner, you would navigate through the grid to collect both keys. The shortest path involves moving right to collect key A, then moving down to unlock the A lock with the A key. From there, you continue downward to collect key B and make your way back. The total number of steps taken is 8, so the output is 8. Breaking down the steps in the first example further, you start at @ in the top left corner. Moving right, you pass through an empty cell to reach the key A. After collecting A, you move downward to unlock the lock A with the key you just acquired. Continuing downward, you reach another lock, B, and move left to collect key B. With both keys in hand, you return to the start by backtracking through previously visited cells. The total number of steps is 8. Now, let's consider a second example. Here, the grid is @B hashtag.B. Starting from it, you move to the right, collecting key A as you go. With the A key, you unlock the A lock. Then, you head down and right to collect key B. The shortest path in this case takes only 6 steps, so the output is 6. Continuing with the second example, after using key A to unlock the A lock, you proceed to collect key B in the bottom right corner of the grid. The total number of steps taken is 6. Now, let's look at a third example. This time, the grid is @a hashtag B. Starting from it, you can see that the lock A blocks the only path to key A. Without the A key, you cannot unlock A, which means the path to the other key B is also inaccessible. Since it is impossible to collect all keys in this scenario, the output is -1. This demonstrates how the presence of walls or locks can make certain keys unreachable, making the task impossible. The constraints for this problem ensure that the grid has at least one row and one column, with a maximum size of 30 by 30. Each cell in the grid will contain one of the specified characters, dot. Hashtag, lowercase letters _F, or uppercase letters _F. The number of keys present in the grid will be between 1 and 6, and each key will have a corresponding lock. Some edge cases to consider include grids with only one row or column, scenarios where certain keys are completely inaccessible due to walls, or cases where backtracking is necessary to find the shortest path. Additionally, you might encounter grids with no walls, which makes all cells accessible, or grids with multiple paths of equal length to collect all the keys. Handling these edge cases effectively will ensure your solution is robust and efficient. To tackle this problem, we first considered a brute force approach. The intuition here is simple: try exploring all possible paths within the grid, collecting keys, and unlocking doors along the way. This could involve recursively trying every possible movement and backtracking as necessary. However, the major drawback of this approach lies in its inefficiency. With up to 6 keys, the number of possible states grows exponentially. Additionally, doors and walls make certain paths inaccessible without the right keys, which means we'd need to carefully track these states. This quickly becomes computationally unfeasible for larger grids. In terms of complexity, this approach would run in exponential time in the worst case, making it impractical for solving this problem efficiently. A more promising approach is to use breadth-first search, or BFS, optimized with state tracking. BFS is well suited for shortest path problems, as it explores all nodes layer by layer, ensuring that the first time we reach a node, it's via the shortest path. Here, we can think of the 2D grid as a graph, where each cell represents a node and adjacent cells are connected by edges. To handle keys and doors, we extend BFS by introducing a concept of state, specifically, the state of collected keys. This state can be efficiently represented using a bit mask. For instance, with 6 keys, a 6-bit integer can track which keys have been collected, such as 001011 indicating that keys B, D, and E are in hand. The process begins at the ith symbol with no keys collected, represented as 000000. At each step, we explore adjacent cells, avoiding walls and locked doors unless we hold the corresponding key. When a key is found, the bit mask is updated to include it. The algorithm terminates once all keys are collected, which corresponds to a bit mask of 11111146 keys. In terms of complexity, the time and space requirements scale as O, n times m times 2 to the power of k, where n and m are the grid dimensions, and k is the number of keys. The 2-k factor accounts for all possible combinations of keys. While BFS with state tracking is already efficient, there are additional optimizations worth considering. One option is to use a priority queue combined with a asterisk search. A asterisk introduces a heuristic, like the Manhattan distance to the nearest key, to prioritize which paths to explore first. This can shrink the search space but comes at the cost of added implementation complexity. Another option is bidirectional BFS, where we simultaneously search from the starting point and the goal state, which is the configuration where all keys are collected. This has the potential to significantly reduce the number of states explored. However, managing the synchronization between the two searches and tracking states for both directions adds complexity. Ultimately, we chose BFS with state tracking for this problem. It is straightforward to implement, guarantees the shortest path due to its layer-by-layer exploration, and handles the key and door constraints effectively using bit masking. While alternatives like A** or bidirectional BFS might offer marginal improvements in specific scenarios, their added complexity outweighs their benefits for grids of this size and constraint. The key insight that made this approach both efficient and practical was the realization that key collection and unlocking doors could be modeled using a bit mask. This drastically simplified state management, reducing the overhead of tracking which keys were held at any given time. By combining this with BFS, we ensure that the shortest path is always found without revisiting redundant states. In terms of complexity, the time and space requirements remain O, n times m times 2 to the power of k, where n and m represent the grid dimensions, and k is the number of keys. This balance of simplicity, efficiency, and correctness makes BFS with state tracking the optimal choice for solving this problem. It avoids the pitfalls of brute force while maintaining a clear and robust implementation. In this problem, we are tasked with navigating a grid to collect all keys while unlocking doors. The grid consists of walls, open spaces, keys represented by lowercase letters from A to F, and doors represented by uppercase letters A to F. Walls block movement, and doors can only be passed if you have the corresponding key. The challenge is to determine the shortest path that allows you to collect all the keys. To solve this, we define each state in the search as a combination of the current position, represented by coordinates x, y, and the keys collected so far, represented as a bit mask. For example, if you've collected keys E and F, the bit mask would look like 000011. This helps track progress efficiently. We use breadth-first search, or BFS, as our main algorithm because it guarantees the shortest path in unweighted grids. The search begins from the player's initial position, and a queue is used to process states in the correct order. To get started, we initialize our data structures, with the queue storing states as tuples of position, keys collected, and the number of steps taken so far. Additionally, we use a visited set to ensure that no state is processed more than once, which prevents redundant computations. Each state in the visited set is represented as x, y, keys underscore collected. This helps us avoid revisiting combinations of positions and collected keys. At the beginning, we enqueue the initial state, which includes the starting position, no keys collected, and 0 steps. Then, the BFS algorithm processes states one by one. For each state, we dequeue the current position, the keys collected so far, and the number of steps taken. If the keys collected match the bit mask that represents all keys, the function returns the number of steps taken as the shortest path. For movement, we explore the 4 possible directions up, down, left, and right. Each potential move is checked to ensure it is within bounds and not blocked by a wall. If the new position contains a key, the bit mask is updated to include that key using a logical or operation. For doors, movement is allowed only if the corresponding key is already in the bit mask, which is checked using a logical and operation. If the new state is valid and hasn't been visited, it's marked as visited and enqueued for further exploration. It's also important to handle special cases to ensure the algorithm works correctly for all inputs. For example, if there are no keys on the grid, the shortest path is 0 steps since there's nothing to collect. If a key is completely inaccessible due to walls or locked doors, the function should return -1, indicating that it's impossible to collect all the keys. Similarly, if the starting position is invalid, such as being inside a wall or outside the grid, the algorithm should handle this gracefully. Finally, if the queue is exhausted without collecting all keys, the function also returns -1, signaling that there's no solution. The algorithm's efficiency is bolstered by several key insights. Using a bit mask to track collected keys is both memory efficient and computationally effective, as it significantly reduces the size of the state space. BFS is ideal for this problem because it guarantees the shortest path, and the use of a visited set eliminates redundant processing, ensuring optimal performance. Together, these elements make the solution robust and efficient. The time complexity of this algorithm is determined by the number of possible states. Each state is represented by a combination of the grid dimensions m and n, as well as the number of keys k. The total number of states is bounded by m times n times 2 to the power of k, since there are 2k possible combinations of collected keys. Each state is processed in constant time, leading to an overall time complexity of m times n times 2 to the power of k. The space complexity is also m times n times 2 to the power of k, due to the storage requirements of the queue and visited set. To further optimize the algorithm, we can prune states that cannot lead to collecting all keys, such as isolated regions of the grid. Additionally, the algorithm includes an early exit condition. Once all keys are collected, the function immediately returns the result, avoiding unnecessary exploration. For example, in the grid.aa/#/BAB, the player starts at and moves to collect key. After unlocking door A, they proceed to collect key B and unlock door B, completing the task in 10 steps. To break down the BFS execution for the example grid, the player starts at position 0, 0, with no keys collected, represented as keys underscore collected equals 0. From there, they move to 0, 1, and then 0, 2, where they collect key, updating the bitmask to keys underscore collected equals 1. Afterward, they backtrack to unlock door A, as the corresponding key is now in their collection. They continue navigating the grid, eventually reaching key B and collecting it, updating the bitmask further. With both keys in hand, they unlock door B and successfully complete the task. The BFS ensures that each step is processed systematically, guaranteeing that the path taken is the shortest possible route to collect all keys. This structured exploration ensures the algorithm is both thorough and efficient, solving the problem within the constraints. Here, we begin by importing the necessary modules. The DEQ from the collections library is used to implement a breadth-first search, or BFS, which is essential for exploring the grid in this problem. Inside the shortest path allkeys function, we first calculate the dimensions of the grid using len, and then initialize two variables, all underscore keys to represent the bitmask of all the keys we need to collect, and start to store the starting position of the player, which is denoted by the @ symbol in the grid. We then iterate through each cell in the grid using nested loops. If the current cell contains we set it as our starting point. If the cell contains a key, identified by lowercase letters A to F, we update the all underscore keys bitmask to include this key using bitwise operations. Next, we define the possible movement directions for navigating up, down, left, and right. After that, we initialize the BFS queue with a tuple representing the starting position, the initial step count of 0, and an empty bit mask indicating no keys have been collected yet. We also use a visited set to keep track of visited states, ensuring we don't revisit the same position with the same collected keys, which helps optimize our search. Finally, the BFS loop begins, where we process each state in the queue. If the current state in the BFS loop has collected all the keys, which we check by comparing keys to all underscore keys, we return the total number of steps taken to reach this state. Otherwise, we iterate through each possible movement direction to calculate the next position. Before proceeding, we ensure the new position is within the bounds of the grid. If the new cell is a wall, denoted by hashtag, we skip it. If the cell is a door, represented by uppercase letters A to F, we check whether we possess the corresponding key. If we don't, we skip this cell as well. If the cell contains a new key, identified by lowercase letters, we update the key's bitmask to reflect that we've collected this key using a bitwise OR operation. After updating the state, we check whether this new state, defined by the position and the updated keys, has already been visited. If not, we add it to the visited set and enqueue it with an increment step count. This ensures that our BFS continues to explore all possible paths while avoiding redundant computations. If the loop completes without finding a state where all keys have been collected, it means that it is impossible to retrieve all the keys given the structure of the grid. In this case, we return -1 to indicate that there is no valid solution. This final return statement ensures that the function handles edge cases where some keys are unreachable due to obstacles or inaccessible areas in the grid. By using BFS, this implementation guarantees that we explore the shortest possible path to collect all the keys, or determine that it cannot be done. To begin our Java implementation, we start by defining the class and method, shortestPathAllKeys. The method takes an array of strings, representing the grid. First, we determine the number of rows and columns in the grid, which will help us navigate through it. We also initialize a bitmask variable, allKeys, to track all the keys we need to collect. Additionally, we define a start array to store the starting position of the player. Next, we iterate through each cell in the grid to locate the starting position, marked as @ and calculate the bitmask for all keys by setting specific bits in all keys. For example, if we encounter a lowercase letter like A, we set the corresponding bit for that key. Finally, we define the movement directions for navigating the grid up, down, left, and right and prepare for a breadth-first search by initializing the queue. We then set up our BFS by initializing the queue and a visited set to avoid revisiting the same state. The queue starts with the initial position, step count set to 0, and no keys collected. The visited set tracks the combination of coordinates and keys by storing them as a string. While the queue isn't empty, we process each state by dequeuing it and extracting the current position, steps taken, and keys collected. If the current set of keys matches all keys, meaning we've collected all the required keys, we return the step count. Otherwise, we explore all possible directions from the current position. For each direction, we calculate the new coordinates and check if they're within bounds. If the new cell contains a wall, represented by hashtag, we skip it. Additionally, we need to ensure that if the cell is a door, we have the corresponding key to pass through. If the cell is a door, we check whether the current keys include the one needed to open it. If not, we skip that cell. On the other hand, if the cell contains a key, we update the keys variable by adding the new key to our collection using bitwise operations. After updating the keys, we check if the new state, defined by the new coordinates and the updated keys, has been visited. If not, we mark it as visited and add it to the queue for further exploration. This ensures that we only explore new states, optimizing our search process. Finally, if the BFS completes without collecting all the keys, it means they are unreachable, and we return -1. This implementation efficiently handles the grid traversal, key collection, and door unlocking to find the shortest path to collect all keys. In this first example, we have a simple one-row grid with no obstacles and a single key. The starting point, marked by @ is at position 0, 0, and the key is at position 0, 2. We initialize the number of rows and columns as 1 and 3, respectively. Since there's only one key, the total bitmask for all keys is 1, calculated as 10. The BFS queue starts with the initial state 0, 0, 0, 0, which means we're at the starting position with 0 steps taken and no keys collected. The visited states initially contain just this starting state, 0, 0, 0. The first step involves dequeuing 0, 0, 0, 0, and exploring its neighbors. Moving right to position 0, 1 is valid since it's an empty cell, so we add 0, 1, 1, 0 to the queue, marking it as visited. Next, we dequeue 0, 1, 1, 0 and explore its neighbors. Moving right again to position 0, 2 is valid, and since this cell contains the key, we pick it up. This updates our collected keys to 1, which is represented in binary as 1. We add the new state 0, 2, 2, 1 to the queue, marking it as visited. Finally, we dequeue 0, 2, 2, 1 and check if we've collected all keys. Since keys equals all underscore keys, the condition is met, and we return the number of steps taken, which is 2. This demonstrates the shortest path to collect all keys in this simple scenario. In this next example, the grid is larger and includes multiple keys and doors. The starting point is at 0, 0, with key at 0, 3, door at 1, 3, and key B at 2, 3. We calculate all underscore keys as 3 because there are 2 keys, A represented as 10 equals 1, and B as 11 equals 2, making the total bit mask 3. The BFS queue starts at 0, 0, 0, 0, and visited states initially include 0, 0, 0. The first step to queues 0, 0, 0, 0, and moving right to position 0, 1 is valid, so we add 0, 1, 1, 0 to the queue. On the next step, we dequeue 0, 1, 1, 0, and move right again to position 0, 2, adding 0, 2, 2, 0 to the queue. From position 0, 2, 2, 0, we move right to 0, 3, where key is located. Picking up this key updates our collected keys to 1. The new state 0, 3, 3, 1 is added to the queue. Next, from 0, 3, 3, 1, we move down to position 1, 3, where door is located. Since we've already collected the matching key, the door unlocks, and we add 1, 3, 4, 1 to the queue. From 1, 3, 4, 1, moving down to position 2, 3 is valid, and this cell contains key B. Collecting this key updates our collected keys to 3, which matches all underscore keys. The new state 2, 3, 5, 3 is added to the queue. Finally, from state 2, 3, 5, 3, we confirm that all keys have been collected, as keys equals all underscore keys. At this point, we return the number of steps taken, which is 5. This example highlights how the BFS algorithm navigates through the grid, unlocking doors and collecting keys in the shortest path possible. In this final example, we have a grid where some keys are unreachable due to locked doors. The starting point is at 0, 0, and there's a door blocking access to key. Here, all underscore keys is 1, as there's only one key. The BFS queue starts with 0, 0, 0, 0, and visited states include 0, 0, 0. From 0, 0, 0, 0, moving right to position 0, 1 is valid, so we add 0, 1, 1, 0 to the queue. However, from 0, 1, 1, 0, moving right to position 0, 2 encounters Dora, which is locked since we don't have the key. With no other valid positions left to explore, the algorithm concludes that collecting all keys is impossible and returns -1. This example illustrates how the algorithm handles scenarios where certain keys are inaccessible. The time complexity of our solution is primarily driven by the breadth-first search, or BFS, traversal of the grid. To understand this, let's define some variables. M represents the number of rows, N is the number of columns, and K is the total number of keys and doors on the grid. Now, each state in the BFS is represented as a combination of 3 elements: the current position, denoted by coordinates x and y, and the keys collected so far, represented as a bit mask. This bit mask helps us keep track of which keys have been collected. Since the problem guarantees a maximum of 6 distinct keys, there are 2 to the power of k, or 2 to the power of k, possible combinations of keys. These are all the potential states we need to consider during the BFS traversal. Now, let's calculate the total number of unique states. To do this, we multiply the total number of positions on the grid, which is m times n, by the total number of possible key combinations, which is 2 to the power of k. This gives us m times n times 2 to the power of k as the maximum number of unique states. For each state, the BFS explores all 4 possible directions: up, down, left, and right. This adds a branching factor of 4. Therefore, the total number of operations required by the BFS is proportional to the product of the number of states and this branching factor. Combining these, the overall time complexity of our solution becomes O of m times n times 2 to the power of k. Now, let's move on to the space complexity. The BFS queue needs to store each state, which includes the current position, the number of steps taken, and the keys collected so far. The maximum size of this queue is proportional to the total number of unique states, which is O of m times n times 2 to the power of k. Additionally, we maintain a visited set to track which states have already been processed, and this also requires O of m times n times 2 to the power of k space. Beyond these, there are a few auxiliary storage needs, such as variables for directions and grid dimensions, but these are negligible compared to the main terms. As a result, the overall space complexity is also O of m times n times 2 to the power of k. To better understand the complexity, let's discuss the best, average, and worst-case scenarios. In the best case, all the keys are located very close to the starting position. Here, the BFS completes after exploring only a small portion of the grid. However, even in this case, the time complexity is still bounded by O of m times n times 2 to the power of k, as that's the worst-case upper limit. In the average case, the BFS explores a moderate number of states before collecting all the keys. And in the worst case, the keys are scattered in the farthest corners of the grid, forcing BFS to explore most of the possible states. In all these scenarios, the time and space complexity remain O of m times n times 2 to the power of k. Now, let's compare our optimized BFS approach with a brute force solution. A brute force method would try all possible permutations of key collection orders and paths. For k keys, there are k factorial permutations, which means the time complexity would grow as O of k factorial times m times n. This becomes computationally infeasible, especially as the number of keys increases. In contrast, the optimized BFS approach avoids redundant exploration. It uses the visited set to ensure that no state is revisited and employs bitmasking to efficiently manage key collection states. This drastically reduces unnecessary computations, making the problem solvable for reasonable grid sizes and key counts. Finally, let's summarize the mathematical justification for our big O analysis. The total number of states is m times n times 2 to the power of k. For each state, BFS processes up to 4 neighbors, which happens in constant time. This leads to a total number of operations proportional to 4 times m times n times 2 to the power of k, which simplifies to O of m times n times 2 to the power of k. On the space side, the dominant factors are the BFS queue and the visited set, both of which also require O of m times n times 2 to the power of k space. In conclusion, both the time and space complexities are O of m times n times 2 to the power of k, where m and n represent the grid dimensions, and k denotes the number of keys. When tackling this problem, it's important to be mindful of a few common mistakes that can trip you up. First, ignoring edge cases is a major issue. For instance, you might encounter empty grids, grids without keys, or situations where keys are unreachable because of locked doors. Failing to address these scenarios can lead to runtime errors or even infinite loops. Another mistake is using inefficient backtracking. A naive approach that explores all possible paths without eliminating invalid or redundant options often results in exponential time complexity, which can cause time limit exceeded errors in larger test cases. Additionally, managing keys and doors incorrectly is a frequent error. This might include forgetting to track which keys have been collected or mishandling duplicate keys, leading the algorithm to attempt unlocking doors without the necessary keys. Lastly, overlooking state optimization can be costly. If you don't store and reuse visited states, such as the combination of position and keys collected, the algorithm ends up re-exploring paths unnecessarily, making it far less efficient. Now, let's discuss improper BFS queue management, which is another common pitfall. In BFS-based solutions, failing to update the queue properly, such as adding duplicate states or neglecting to mark states as visited, can lead to redundant computations and incorrect results. Shifting gears to the interview setting, it's essential to thoroughly understand the problem constraints. For example, clarify the grid size, the number of keys indoors, and how edge cases should be handled. What happens if no solution exists? These are important questions to ask. Additionally, optimizing early in your thought process can set you apart. For instance, consider BFS with state tracking or bit masking right from the start to demonstrate a deeper understanding of the problem. Clear communication is also key. When explaining your approach, focus on how you manage state, such as tracking collected keys, and how you prune unnecessary paths. Use examples to illustrate your strategy and show how your solution avoids redundant work. Finally, make sure to test your solution thoroughly. Run it against a variety of edge cases, including the smallest grids, grids without keys, and even grids where all doors are already unlocked. This problem shares similarities with several related challenges, which can provide valuable practice. For example, LeetCode 864 itself focuses on collecting all keys, while LeetCode 1293 tackles navigating a grid with obstacles that can be eliminated. Similarly, LeetCode 847 involves visiting all nodes in a graph, and LeetCode 752 explores unlocking a combination lock. Each of these problems emphasizes pathfinding under different constraints, making them great for building complementary skills. Now, when it comes to alternative approaches, a brute force backtracking method might seem straightforward and simple to implement. However, it's highly inefficient and only suitable for very small grids. A more effective solution is BFS with state tracking, which is well suited for finding the shortest path but does require additional memory to store visited states. Bit masking is another option, particularly for managing keys. It reduces memory usage by representing key states compactly, but it does add complexity to your implementation. Finally, there's the A** search algorithm, which is another powerful alternative. This method incorporates heuristics to optimize pathfinding, making it especially effective for certain types of problems. However, it can be overkill for simpler scenarios, where the added complexity isn't justified. Choosing the right approach ultimately depends on the specific constraints and requirements of the problem you're solving. Balancing efficiency, memory usage, and implementation complexity is key to developing a robust and scalable solution. Great job! To summarize, we tackled the shortest path to get all keys problem using BFS with state tracking for efficiency. We learned key insights about managing dynamic constraints and optimizing grid-based problems. Thanks for watching. Be sure to like, subscribe, and stay tuned for more coding challenges. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!